Alright, time to read about some gears. Try not to be too boring, but the point is to just name the equations. Don't need to talk about them too much, but go through the principles and see if we can squeeze anything out of this. This is page 665, which is where we are, up to 706. That is, it's a fair amount of pages, so we begin. This chapter addresses gear geometry, the kinematic relations, and the force transmitted by the four principal types of gears: spur, helical, bevel, and worm gears. The forces transmitted between meshing gears supply torsional moments to shafts for motion and power transmission and create forces and moments that affect the shaft and its bearings. The next two chapters will address stress, strength, safety, and reliability of the four types of gears. 13-1 Types of gears. Spur gears, illustrated in figure 13-1, have teeth parallel to the axis of rotation and are used to transmit motion from one shaft to another. Parallel shaft. Of all types, the spur gear is the simplest and, for this reason, will be used to develop the primary kinematic relationship of the tooth form. Helical gears, shown in figure 13-2, have teeth inclined to the axis of rotation. Helical gears can be used for the same applications as spur gears and, when so used, are not as noisy because of the more gradual engagement of the teeth during meshing. The inclined tooth also helps thrust loads and bending couples, which are not present with spur gearing. Sometimes helical gears are used to transmit motion between non-parallel shafts. Bevel gears, shown in figure 13-3, have teeth formed on conical surfaces and are used mostly for transmitting motion between intersecting shafts. The figure actually illustrates straight-tooth beveled gears. Spiral bevel gears are also cut, so the tooth is no longer straight, but forms are a circular arc. Hypoid gears are quite similar to spiral bevel gears, except that the shafts are offset and non-intersecting. Figure 13-1, spur gears are used to transmit rotary motion between parallel shafts. Those shafts are parallel and rotary motion in opposite direction. Now, helical gears are used. Okay, so we have an angle to the cut. Alright, and he said something about something. I don't know, same deal as the other one. And then bevel gears, alright, rotary motion between intersecting shafts. And the cat is getting up. Hisman, that's a microphone. Okay, Baba, I need to see the screen. Move, please. Okay, I move you. Or I look around you. Alright. Worm gear sets are used to transmit rotary motion between non-parallel, non-intersecting shafts. Non-parallel, so those are... Alright, so those are like skew lines, kind of. Worms and worm gears, shown in figure 13-4, represent the fourth basic gear type. As shown, the worm resembles a screw. The direction of the rotation of the worm gear, also called the worm wheel, depends upon the direction of rotation of the worm and upon whether the worm teeth are cut right or left-handed. Worm gear sets are also made so that the teeth of one both wrap partly around the other. Such sets are called single enveloping and double enveloping worm gear sets. Worm gear sets are mostly used when the speed ratios of the two shafts are quite high, say 3 or more. 13.2 Nomenclature. The terminology of spur gear teeth is illustrated in 13-5. The pitch circle is a theoretical circle upon which all calculations are usually based. Its diameter is the pitch diameter. The pitch circles of a pair of mating gears are tangent to each other. A pinion is the smaller of the two mating gears. The larger is often called the gear. The circular pitch P is the distance measured on the pitch circle from a point on one tooth to a corresponding point on an adjacent tooth. Sounds like a wavelength to me. Thus, the circular pitch is equal to the sum of the tooth thickness and the width of the space. Alright, let's take a look. If the face width, that's sort of the top of the gear, front to back. If you've got a disc, if it's just a coin, how thick is that coin? That's the with the top land is the flat part of each tooth on top, on the outermost part. The addendum, let's see, what is this going to, what is this line? Hello, anyone? Yeah, nobody's there when you're talking to yourself. All right. Dedendum, whatever. Addendum is top. Dedendum is closest to the center. Tooth thickness is, there's a line between that separates the addendum from the dedendum. Circular pitch, let's see. Pitch circle, maybe, that must be the pitch circle. All right. And how did they oh, balls. That was way too far. All right. Nomenclature, pitch diameter. Pitch circle is this theoretical circle. Its diameter is the pitch diameter. It's where they're, all right. Okay. So when these two gears, all right. So that's the reason it's right there. The thing is, when the other gear touches it, it's going to be tangent. They're going to be, that's where they're going to be touching. And the force is going to be at whatever angle is between those, probably 20 or so. The module M is the ratio of the pitch diameter to the number of teeth. So M is just a ratio, pitch diameter to how many teeth. So if it's really big and has 2 teeth, that's not going to work. All right. The customary unit of length used is the millimeter. The module is the index of the tooth size in SI. The diametral pitch, capital P, that's the diametral pitch, capital P. The lowercase p was the circular pitch. Alright, so pitch circle, do we see diametral pitch on there? I don't. Do you? Are you watching? Alright. Diametral, do we have another graph? No. So I must just be missing things because I certainly don't see it. Whatever. Capital P is the ratio of the number of teeth on the gear to the pitch diameter. Thus, it is the reciprocal of the module. Since the diametral pitch is used only with US units, it is expressed as teeth per inch. Capital P is teeth per inch. The addendum A is the radial distance between the top land and the pitch circle. The dedendum B is the radial distance from the bottom land to the pitch circle. The whole depth, W-H-O-L-E, whole depth, H sub T, is the sum of the addendum and the dedendum. The whole depth. Where is that? A lot of things aren't labeled here, are they? All right. You should prove for yourself. You should prove for us. Pay for the book or click download. You should prove for yourself the validity of the following useful relations. P equals N over D. Did we say what? N must be number of teeth. Over D diametral. That's circular pitch. Yeah. Little p, circular pitch. M is D over N number. P is pi D over N. Pi D is 2 pi R, which is circumference. And that is pi M. Yeah, okay, all those. Yeah, this equals that. Got it. Number of, okay, module. Okay, P equals diametral. Capital P, big P. I guess we'll have. Strong. All right, capital P is diametral pitch, teeth per inch. N equals number of teeth. D equals pitch diameter, or inches, or inches or millimeters. M is module in millimeters, and P is circular pitch in inches or millimeters. And what I was just trying to figure out how to say capital P or big P without saying capital P or big P. I just wanted to distinguish the two different ones. I want to call it P dot. So P dot will now be the diametral pitch. 13.3 Conjugate action. The following discussion assumes the teeth to be perfectly formed, perfectly smooth, and absolutely rigid. Such an assumption is, of course, unrealistic because the application of forces will cause deflections. Mating gear teeth acting against each other to produce rotary motion are similar to cams. When the tooth profiles or cams are designed so as to produce a constant angular velocity ratio during meshing, they are said to have conjugate action. In theory, at least, it is possible arbitrarily to select any profile for one tooth and then to find a profile for the meshing tooth that will give conjugate action. One of these solutions is the Involute profile, which, with few exceptions, is in universal use for gear teeth and is the only one which we will be concerned. Yay, good to know. I made one in sculpture class the other day. When one curved surface pushes against another, the point of contact occurs where the two surfaces are tangent to each other, point C, and the forces at any instant are directed along the common normal AB to the two curves. Line AB, representing the direction of action of the forces, is called line of action. The line of action will intersect the line of centers OO at some point P dot. The angular velocity ratio between the two arms is inversely proportional to their radii to the point P. Circles drawn through to the point P dot. Circles drawn through point P dot from each center are called pitch circles, and the radius of each circle is called the pitch radius. Some point P dot, which is called the pitch point. Point P dot is called the pitch point. Figure 13.6 is useful in making another observation. A pair of gears is really a pair of cams that act through a small arc before running off the involute contour are replaced by another identical pair of cams. The cams can run in either direction and are configured to transmit a constant angular velocity ratio. If involute curves are used, the gears tolerate changes in center-to-center distance with no variation in constant angular velocity ratio. Furthermore, the rack profiles are straight-flanked, making primary toothing simpler. To transmit motion at a constant angular velocity ratio, the pitch point must remain fixed. That is, all the lines of action for every instantaneous point of contact must pass through the same point P. In the case of the involute profile, it will be shown that all points of contact occur on the same straight line AB, that all normals to the tooth profiles at the point of contact coincide with the line AB, and thus that these profiles transmit uniform rotary motion. Cam A and follower B in contact when the contacting surfaces are involute profiles. The ensuing conjugate action produces a constant angular velocity ratio. Alright. So omega 1 over omega 2 is constant. Opposite directions again. Something. Alright, so the generation of an involute. Hey, Boba. Base. Let's see. There's a base circle. There's a pitch circle. Base circle. Pitch circle. Alright, pitch circle. Base circle on gear 2. And 13.4 involute properties. An involute curve may be generated as shown in figure 13.7a. A partial flange B is attached to the cylinder A, around which is wrapped a chord def. What does that mean? Chord def. Anyways, which is held tight. Point B on the chord represents the tracing point. As the chord is wrapped, point B represents the tracing point. Okay. Gotcha. Alright. I think I gotcha. Maybe. Alright, D. Partial flange B is attached to cylinder A, which is wrapped around chord def, which is held tight. Move, kitty. Point B on the chord represents the tracing point. Oh, no, I'm moving that away. Ow. Okay. And as the chord is wrapped around is wrapped and unwrapped around the cylinder, point B will trace out the involute curve arc. The radius of the curvature of the involute varies continuously, being 0 at point A and a maximum at point C. Alright, 0 at point A, maximum point C. Alright, so you're holding that. And what is it attached to F? Where is it held? Okay. But whatever, so you go, this string is here, and you unwind it, and you got a pen in there, and you're tracing it. And if you just keep going, guess what? It's going to give you a bigger and bigger spiral. Okay. Right, that's what happened at the end. Okay, and then alright, you see, I made this in sculpture class the other day, and I started from the very outside and came all the way in. It was just like, it looked like a regular spiral, but each time it came in, it just went just like that, and that is perfect, and that makes sense. And then you go on the other side. Looks kind of weird though. Alright, now, all right, now, do you get it? Okay, you got this string coming around, and that's the string, but you jam a pen in here, right? And then you just it's jammed in there, so it can't go anywhere but to follow the path that the string wants to at that point. Anyways, I'm sure you get it. And if you don't, well, I'm probably the only one listening to this, and I get it, so I do. The radius of the curvature of the involute varies continuously, being 0 at point A and A maximum at point C. At point B, the radius is equal to the distance BE, since point B is instantaneously rotating about point E. Thus, the generating line DE is normal to the involute at all points of intersection and, at the same time, is always tangent to the cylinder A. I don't even know what I'm reading right now. The circle on which the involute is generated is called the base circle. Let us now examine the involute profile to see how it satisfies the requirement for the transmission of uniform motion. In figure 13-7b, two gear blanks with fixed centers at O1 and O2 are shown having base circles whose respective radii are O1a and O2b. We now imagine that a cord is wound clockwise around the base circle of gear 1, pulled tight between points A and B, and wound counterclockwise around the base circle of gear 2. If now the base circles are rotated in different directions so as to keep the cord tight, a point G on the cord will trace out the involutes CD on gear 1 and EF on gear 2. The involutes are thus generated simply by the tracing point. The tracing point therefore represents the point of contact, while the portion of the line cord AB is the generating line. You getting this? Might have to rewind. The point of contact moves along the generating line. The generating line does not change position because it is always tangent to the base circles, and since the generating line is always normal to the involutes at the point of contact, the requirement for uniform motion is satisfied. 13.5. Fundamentals. Among other things, it is necessary that you actually be able to draw the teeth on the mesh on a pair of meshing gears. You should understand, however, that you are not doing this for manufacturing or shop purposes. Rather, we're making drawings of gear teeth to obtain an understanding of the problems involved in the meshing of the mating teeth. Get it? You're not making new gears. You just got to get the gears in your brain. That's like the symbol of thinking hard. So get it. Construction of an involute curve. Diaz, you make us all say your things. It's easy. Okay. Frobenius method. First, it is necessary to learn how to construct an involute curve. As shown in figure 13.8, divide the base circle into a number of equal parts and construct radial lines OAO, OA1, OA2, OA, etc. Beginning at A1, construct perpendiculars A1, B1, A2, B2, A3, B3, etc. And then along A1, B1, lay off the distance A1, AO, along A2, B2, lay off twice the distance A1, AO, etc., producing points through which the involute curve can be constructed. To investigate the fundamentals of tooth action, let us proceed step by step through the process of constructing the teeth on a pair of gears. Let's see. To investigate the fundamental pair of gears. All right. Sorry, I was just checking my other computer. When the two gears are in mesh, their pitch circles roll on one another without slipping. Designate the pitch radii as R1 and R2 and the angular velocities omega1 and omega2 respectively. Then the pitch line velocity is V equals the magnitude of R1 omega1 equals R2 omega2. Thus, the relation between the radii on the angular velocities is omega1 over omega2 equals R2 over R1. Yeah, so we lost the magnitude there somewhere, but I'm sure that's fine because R's are always positive and omegas can be negative. Suppose now we wish to design a speed reducer such that the input speed is 1800 revs per minute and the output speed is 1200 revs per minute. This is the ratio 3:2. The pitch gear diameters would be in the same ratio. For example, a 4-inch pinion, that's the small one, driving a 6-inch gear, that's the big one. The various dimensions found in gearing are always based on the pitch circles. Suppose we specify that an 18-tooth pinion is to mesh with a 30-tooth gear and that the diametral pitch of the gear set is to be 2 teeth per inch. Then, from equation 13.1, the pitch diameters of the pinion and gear are respectively d1 equals n1 over p, 18 over 2, equals 9 inches. d2 equals n2 over p, which is 30 over 2, and that is, guess what, 15. That's because 30 divided by 2 is 15 inches. Inconsistent labeling of units there, I have to say. Very disappointed. The first step in drawing teeth on a pair of mating gears is shown in figure 13.9. The center distance is the sum of the pitch radii in the case of 12 inches. In this case, 12 inches. So locate the pinion and gear centers O1 and O2, 12 inches apart. Then construct they really should be like superscripted or subscripted or italicized because it looks, I see in every time. Then construct the pitch circles of radii R1 and R2. These are tangent at P dot, the pitch point. Next, draw line AB, the common tangent through the pitch point. We now designate gear 1 as the driver, and since it is rotating counterclockwise, we draw a line CD through point P dot at an angle phi to the common tangent AB. The line CD has 3 names. Oh, great. All of which are in general use. It's called the pressure line, the generating line, and the line of action because one name wasn't enough. It represents the direction in which the resultant force acts between the gears. The angle phi is called the pressure angle, and it usually has values of 20 or 25 through 14 and 1/2 degree. 3 more, right? Because I guess we like doing things in threes and saying that it happens all the time in these ways, except when it doesn't. That they were all once used, and now we use something special. Did we already say what it always is now? What is it, 30? 20? 30? I don't know. Okay. The addendum, pitch circle, base circle, involute, addendum circles, B, D, pitch circle, pressure line. Yeah. That's one of the 3 names. Next, on each gear, draw a circle tangent to the pressure line. These circles are the base circles. Since they are tangent to the pressure line, the pressure angle determines their size. As shown in figure 13.10, the radius of the base circle is RB. That's radius of the base circle equals R cosine phi, where R is the pitch radius. Now, generate an involute on each base circle as previously described and as shown in figure 13-9. This involute is to be used for one side of a gear tooth. It is not necessary to draw another curve in the reverse direction for the other side of the tooth. Why? Because we are going to use a template. Duh. Why didn't we just use a gear template to begin with? Sorry. We're going to use a template which can be turned over to obtain the other side. Perfect. The addendum and the dedendum distances for standard interchangeable teeth are, as we shall learn later, or now, 1 over p and 1.25 over p, respectively. We learn that like this second. Therefore, for the pair of gears, we are constructing A equals 1 over p equals 1/2 equals 0.500 inches. Inconsistency in significant figures. I tell you, I'm very disappointed. B equals 1.25 over p dot. Oh, I'm not consistent with my p dot. So hopefully you are looking and not just listening. 1.25 over 2 equals 0.625 inches. Using these distances, draw the addendum and dedendum circles on the pinion and on the gear shown in figure 13.9. Next, using heavy drawing paper or preferably stone or a sheet of 0.015 to 0.020 inch clear plastic, cut a template for each involute. Really? All right, let's do the arts and crafts. Let's do this. This is fun. Being careful. Where's some scissors? All right, we're good to go. Yeah, where were we? Gears properly cut. Where was I? Cut. There we go. Cut a template for each involute. Being careful to locate the gear centers properly, of course, with respect to each involute. Figure 13.11 is a reproduction of the template used to create some of the illustrations in this book. Note that only one side of the tooth profile is formed on the template. Yeah, because we mentioned that. You can flip it to get the other side. Turn the template over. Oh, yeah. For some problems, you might wish to construct a template for the entire tooth. Yeah, I would. That makes sense, right? That would be a better template, don't you think? I think so. Anyways, figure 13.11, template for drawing a gear. We should really do this. Tooth action. You don't want tooth action. You just want your teeth to stay in place. Dedendum circle, base circle, pitch circle, addendum circle, angle of recess, angle of approach, and let's see, do we have a turning direction? So how do you know which one's the approach? Approach, angle of recess. Okay, so coming in, coming out, I don't know how to tell. Coming in, touching, going out, leaving. I see, it's deeper in there. You see that? You see that? The angle of approach, it's the angle of contact is far deeper in this gear. And then as it's pushing away, it's down there. Interesting. What would it be the same coming back? I don't know, you figured out. Gear driven. Yeah, there's the turning direction. Okay, there's O2 down here in the gear, O1 in this pinion. Alright, to draw, hey look, I'm learning. Go figure. Can happen. Can happen to you. Dream big. To draw a tooth, we must know the tooth thickness. From equation 13-4, the circular pitch is P equals pi over P dot equals pi over 2 equals 1.57. Therefore, the tooth thickness is T equals P over 2, 1.57 over 2. Of course, that's 0.785. Totally did that in my head before they even got there. Okay, maybe not. Measured on the pitch circle. Using this distance for the tooth thickness as well as the tooth space, draw as many teeth as desired. Full set of teeth would be great. Using the template after the points have been marked on the pitch circle. In figure 1312, only one tooth has been drawn on each gear. You may run into trouble. Oh, right. I can keep reading. I will run into trouble in drawing these teeth if one of the base circles happens to be larger than the dedendum circle. Okay, so watch out for that. The reason for this is that the involute begins at the base circle and is undefined below it. So in drawing gear teeth, we usually draw a radial line for the profile below the base circle. Got it? The actual shape, however, will depend upon the kind of machine tool used to form the teeth in manufacture. That is how the profile is generated. The portion of the tooth between the clearance circle and the dedendum circle includes the fillet. In this instance, the clearance is C equals B minus A. Equals 0.625 minus 0.5 is 1.25, or 0.125 inches. The construction is finished when the fillets have been drawn. Referring to the figure 1312, the pinion with center O1 is the driver and turns counterclockwise. The pressure or generating line is the same as the cord used in figures 13.7a to generate the involute, and contact occurs along this line. The initial contact will take place when the flank of the driver comes to the contact with the tip of the driver tooth. This occurs at point A in figure 1312, where the addendum circle of the driver gear crosses the pressure line. If we now construct tooth profiles through point A and draw radial lines from the intersections of these profiles with the pitch circles to the gear centers, we obtain the angle of approach for each gear. As the teeth go into mesh, the point of contact will slide up the side of the driving tooth so that the tip of the driver will be in contact just before contact ends. That's okay. The final point of contact will therefore be where the addendum circle of the driver crosses the pressure line. You got it? This is point B, figure 1312. By drawing another set of tooth profiles through B, we obtain the angle of recess for each gear in a manner similar to that of finding the angles of approach. The sum of the angle of approach and the angle of recess for either gear is called the angle of action. That's the total. That's the sum. The line AB is called the line of action. We may imagine a rack as a spur gear having an infinitely large pitch diameter. Therefore, the rack has an infinite number of teeth in a base circle, which is an infinite distance from the pitch point. What is this? Like a rack is like a straight gear or something? Just a flat thing with some gear, some like teeth on it? Must be. The sides of the involute teeth in a rack are straight lines, making an angle to the line of centers equal to the pressure angle. Figure 1313 shows an involute rack in mesh with a pinion. Corresponding sides of an involute teeth in parallel curves. The base pitch is the constant and fundamental distance between them along common normal, as shown in 1313. The base pitch is related to the circular pitch by this equation: PB, base pitch, equals PC, circular pitch, something, cosine of phi. So PB equals PC cosine phi. where PB is the base pitch. 13.4 shows opinion in mesh with internal or ring gear. Note that both of the gears now have their centers of rotation on the same side of the pitch point. Thus, the positions of the addendum and dedendum circles with respect to the pitch circle are reversed. The addendum circle in the internal gear lies inside the pitch circle. Note, too, from figure 13.14, that the base circle of the internal gear lies inside the pitch circle near addendum circle. Another interesting observation, interesting is a relative term, keep that in mind. Another interesting observation concerns the fact that the operating diameters of the pitch circles of a pair of meshing gears need not be the same as the respective design pitch diameters of the gears. Got it? Though this is the way they have been constructed in 1312. If we increase the center distance, we create two new operating pitch circles having larger diameters because they must be tangent to each other at the pitch. Base pitch, circular pitch. Anybody following along with what I just said? Am I? Do I know? I don't know. Pitch circle, pressure line, dedendum circle. A nice time to take a look at these things that we've been talking about. Omega 2, O2, base circle, pitch circle, addendum circle. Alright, so the last words I said. If we increase the center distance, we create two new operating pitch circles having larger diameters because they must be tangent to each other at the pitch point. Thus, the pitch circles of gears really do not come into existence until the pair of gears are brought into mesh. Just making sure I unpaused it. Had to pause it for a second. Alright. So, I should have just said, thus the pitch circles of gears really do not come into existence until a pair of gears are brought into mesh. Gotcha. And the mesh is in there when they come together. Changing the center distance has no effect on the base circles because these were used to generate the tooth profiles. So changing the center distance has no effect on the base circles because these were used to generate the tooth profiles. Thus, the base circle is basic to a gear. Increasing the center distance increases the pressure angle and decreases the length of the line of action, but the teeth are still conjugate. The requirement for uniform motion transmission is still satisfied. Interesting. I don't know what they mean, but it sounds very important. It sounds like it's very useful. And the angular velocity ratio has not changed. All right, 13.1. A gear set consists of 16-tooth pinion driving a 40-tooth gear. The diametral pitch is 2. The addendum and dedendum are 1 over p and 1 over p dot and 1.25 over p dot, respectively. The gears are cut using a pressure angle of 20 degrees. Maybe that's the thing that we said earlier when we had 3 choices, and I thought it was 20 maybe. Compute the circular pitch, the center distance, and the radii of the base circles, and also you were tasked with, in mounting these gears, the center distance was incorrectly made 1/4 inch larger. Compute the new values of the pressure angle and pitch circle diameters. So, first you know that P equals pi over P, and little p equals pi over P, and P dot is 2, so pi over 2. So little p is pi over 2, 1.571 inches. The pitch diameters of the pinion and gear are respectively dp equals np over p dot equal np 16, so it's 16 tooth over p. Where do we see the diametral pitch? So the capital P diametral pitch is 2, so 16 over 2 is 8. And then the dg ng over p ng 42, so that's 40 tooth over p is the same. Over 2 is 20. Therefore, the center distance is dp plus dg over 2. That's 28 over 2, which is 14. Since the teeth were cut on a 20-degree pressure angle, the base circle radii are found to be using RB equals R cosine of phi. RB pinion equals 8 over 2 cosine. Alright, I'm getting tired, so maybe we'll cut this short. Try to get through this. Maybe do contact ratio. Since the teeth were cut on a 20-degree pressure angle, the base circle radii are found to be RB equals R cosine of phi. RB pinion equals 8 over 2 cosine of 20 degrees. RB pinion. So 8 over 2, what are we just saying for? RB pinion, screen not working. Move. Can't drag it with my hand. Alright, screen's getting tired too. Like, I can't. I don't know what I did, but I can't drag it. It's a touch screen, it's not responding. We'll just go through this. Maybe we'll understand it by the time we get there. RB pinion. So I guess we mentioned it earlier, right? Yeah, we did. And the RB gear 20 over 2, 8 and 20. What's this? 8 and 20. We got an 8 somewhere and a 20. Yeah, the DP. All right. So it's DP over 2 cosine 20 in each thing. DP and then DG. All right, gotcha. Then be designating D prime P and D prime G as the new pitch circle diameters. The 1/4 inch increase in the center distance requires that D prime P plus D prime G over 2 equals 14.25 because 1/4 inch longer. That's 0.25 inch larger. And larger than center distance. Where did we say the center distance was 14? Do we have like a 14 or 28? We got a 28 center distance, right? I guess 40. There we go. Therefore, the center distance is 14. Yeah. So now it's 14.25. Also, the velocity ratio does not change, and you don't say and, you just say hence. The velocity ratio does not change. Hence, d prime p over, see, that sounds better, over d prime g equals 16 over 40. Solving equations 1 and 2 simultaneously, and like a juggler, d prime p equals 8.143, d prime g equals another number, gives a, what do we solve? What equations 1 and, okay, just these two, that's it. Okay, alright, just solve those, and then you get d prime p, d prime g, and then you go and let's see, you want phi, so RB equals R cosine phi. Using either pinion or gear, we can find phi. And so for both of them, that's going to be the arc cosine RB pinion over d prime p over 2. And that's the same as arc cosine of RG, I think. No, this is the pinion. Over 8.143 over 2. All right, sorry I got sloppy in the end. Maybe I can read one more before I pass out. Let's just read a little bit of this. This might get loopy. So whatever. You're listening to this, so that's on you. You could have stopped at any point before now, but here you are. 13.6 contact ratio. The zone of action of meshing gear teeth is shown in figure 13.5. We recall that tooth contact begins and ends at the intersections of the two addendum circles with the, hey kitty. Okay, I wasn't talking to you and I said you could have stopped at any time, Bubba. Come here. Come on, it's almost over. This is one last thing. Alright. Yeah, I'm getting yelled at because it's definitely time to sleep. And cats like to sleep. The zone of action of meshing gear teeth is shown in 13.5. We recall that the tooth contact begins and ends at the intersections of the two addendum circles with the pressure line in figure 13.5. Initial contact occurs at A and final contact at B. Tooth profiles drawn through these points intersect at pitch circle A and B respectively. As shown, the distance AP is called the arc of approach. QA, that's question and answer in some circles. Arc of approach here though. Q, why is it Q? I don't know. Whatever, it's Q. Arc of approach is now Q. Got it? Done. And the distance PB, the arc of recess QR. So QA is arc of approach, arc of research is recess. The sum of these is the arc of action QT. Now, consider a situation in which the arc of action is exactly equal to the circular pitch, that is QT equals P. That means that one tooth and its space will occupy the entire arc AB. In other words, when a tooth is just beginning to contact A, the previous tooth is simultaneously ending its contact at B. Therefore, during the tooth action from A to B, there will be exactly one pair of teeth in contact. Did you know that if you have a gear inside of another gear, it helps something like that? So you can have more teeth engaging at once? Anyways, check out the gravity light if you want to know what I'm talking about. from Devin from Smarter Every Day. All right. Next, consider a situation in which the arc of action is greater than the circular pitch, but not very much greater. Really? Did they just do that? Say 1.2 p. This means that when one pair of teeth is just entering contact at A, another pair already in contact will not yet have reached B. Thus, I had to use thus in a sentence today, part of a test. Took one of those. Thus, for a short period of time, there will be two teeth in contact, one in the vicinity of A and another near B. As the meshing proceeds, the pair near B must cease contact, leaving only a single pair of contacting teeth until the procedure repeats itself, like Groundhog Day. Because of the nature of this tooth action, either one or two pairs of teeth in contact, it is convenient to define the term contact ratio M sub C as M sub C equals QD over P. Yeah, McQDP. Alright. McQDP. McQDP. Alright. I don't know. I really should have stopped. Am I still working? Guess paycheck. 1 second. I'll be right there. A number that indicates the average number of pairs of teeth in contact. Note that this ratio is also equal to the length of path of contact divided by the base pitch. Gears should not generally be designed having contact ratios less than about 1.20, because inaccuracies in mounting might reduce the contact ratio even more. No, increasing the possibility of impact between the teeth as well as increase in noise level. Bummer. Don't do that. Okay, just stick with these rules. An easier way to obtain the contact ratio is to measure the line of action AB instead of the arc distance AB. Since AB in figure 1315 is tangent to the base circle when extended, the base pitch PB must be used to calculate MC instead of the circular pitch as in equation 13.8. If the length of the line of action LAB is the contact LAB, the contact ratio is MC lab over P cos phi. Sorry, M sub C equals L sub AB over P cosine phi, in which equation 13.7 was used for the base pitch. Thanks for listening. Good luck studying 13.7, maybe later.